In section 6.2, our goal is to solve differential equations and apply them to real-life problems. We want to be able to use exponential functions to model growth and decay. Recall that direct variation is written as y equals k times x if y and x vary directly. Inverse variation is y equals k over x if y and x vary inversely. Another way to describe the direct variation is by saying that y is proportional to x. So when one value gets bigger, the other one does as well. Let's translate the statement. The rate of change of y is proportional to y. We're often going to see this. First of all, rate of change. Remember that that means derivative. And normally in these real-life problems, it's going to be the derivative with respect to time. So the rate of change of y will be the derivative of y with respect to time. How that's written? dy dt. Is translates into an equal sign, proportional to y. So if y is proportional to x, it's equal to a constant times the thing it's proportional to, a constant times x. Here, it's proportional to y, so a constant times y. This is a differential equation. This differential equation is going to be a very important one that we're going to use a lot because a lot of growth and decay models are modeled by this differential equation. So this translates into this, and we have to know that. Now the solution to this will always look like something that we can simply memorize. The solution is y equals ce to the kt, an exponential function. This is the solution to our differential equation. Now I don't like you to just memorize it and that's it. I'd like you to know where it comes from. So let's retrace our steps in solving a differential equation. dy dt equals k times y. Remember, the first step is separating our variables. In this case, the variables are y and t. So I'll move my y over, and that'll make dy over y, and I'll move the dt by multiplying k times dt. Remember that k is a constant. In this case, it's the constant of proportionality. I will integrate both sides, the integral of 1 over y dy and the integral of k dt. This one makes the natural log of the absolute value of y. On this side, it makes k times t plus c. I don't like to leave the natural log. I'd like to get the y by itself. So I will exponentiate both sides with base e. This becomes the absolute value of y equals e to the kt times e to the c. Well, we know that taking away the absolute value symbols is going to require placing a plus or minus in front of that side or the other side. If I'd like to let my constant e to the c absorb the plus or minus, I can rewrite it like this: y equals c e to the kt. Now, every time you could solve this differential equation, but that would really be a waste of time. And since the exponential growth and decay model is usually modeled by this differential equation, we should just memorize that this is the solution. So memorize that this differential equation we're going to be using a lot, and this solution is what we would always have. The c, well, what can we say that represents? Let's take a look at what it means if I say c is the initial value of y. Initial value, well, what does that mean? Initial value, that means at time 0, at the initial time when we start counting 0. So if I plug 0 into this equation right here, y equals ce to the k times 0. Instead of y, I'm going to call that the initial amount, or y sub naught. Well, e to the 0 is just 1, and therefore y sub naught, the initial y, equals c. c is the initial value of y. K represents what I said earlier, the constant of variation also known as the constant of proportionality. If k is positive, this equation represents exponential growth, where graphically it looks like this. And if k is negative, the equation represents exponential decay, where the graph looks something like that. Let's explore some examples that test this knowledge. AP problem. If dy dt equals ky, this should look familiar. It's that popular differential equation where we use for growth and decay. And k is a non-zero constant, then y could be, well, first let's determine if I know this differential equation, I will know the solution, y equals ce to the kt. So I'm looking for the solution that looks like this. Have you identified it? It's not this one. That has an extra variable in the exponent. Did you pick choice B? That's the one. The 2 is in place of our c, and that's a constant, and e to the kt. Y could equal ce to the kt, 2e to the kt. Not adding anything, and definitely not without the e, the exponential function. Let's look at number 2. The rate of change of y is proportional to y. Well, that should look familiar right off the bat. Immediately we know rate of change of y, dy dt, is proportional, constant of proportionality, is proportional to y. When t equals 0, y equals 2. When t equals 2, y equals 4. What is the value of y when t equals 3? So first thing we're going to do, we have a differential equation. Immediately we're going to write the solution. Hopefully we don't have to waste our time separating the variables and integrating all over again. Now, if we need to figure out ultimately what is the value of y when t equals 3, I need to know what these constants are. I don't have the constants. So like we've done earlier in differential equations, I'm going to use an initial condition to help me find the constants. But if I have 2 constants to find, I have 2 initial conditions that I have to use. Let's take it one at a time. Let's start by using t equals 0 and y equals 2. Y equals 2 and t equals 0. And let's see where that takes us. E to the 0, that's 1. So c equals 2. Well, that wasn't too bad. Now I have y equals 2e to the kt. Let's go to the second initial condition. T equals 2 when y equals 4. So now from here, y is 4 and t is 2. 2e to the k times 2. I need to get the e to go away, but first I have to get the 2 away from the e. So I'm going to divide by 2, and I get 2 equals e to the 2k. If I have to make the e go away, I'm going to take the natural log, and therefore I have to do it of both sides. Natural log of 2 and natural log of e to the 2k. This side has to remain natural log of 2. This side, the natural log of e, leaves just the exponent of 2k. Now I can solve for the k. Divide both sides by 2, and k equals natural log of 2 divided by 2. Or perhaps we'd rather write it as 1/2 natural log of 2. Now we're going to plug it in and rewrite our equation. So remember, y equals c to the kt became y equals 2e to the kt. I know c is 2, and the k is 1/2 natural log of 2, and then times t. But I can simplify that. First, I'm going to do some rearranging. If I'm multiplying 1/2 times natural log of 2, I can switch those places, and it's still the same thing. Y equals 2e to the natural log of 2 times 1/2, and then times t. Then, because the e and the natural log are inverses of each other, I can just bring that 2 down as the new base. So what does that look like? Y equals 2 times 2, this base right here, to the 1/2 t. And that's much simpler. Now I'm going to go to the final question. What is the value of y when t equals 3? So when t equals 3, it looks like this. So 2 times 2 to the 3/2. And then I can add these exponents, 2 to the 1 and 2 to the 3/2. 1 plus 3/2 is 5/2. So 2 to the 5/2. That's probably the best answer I could give, so I'll stop there. A lot of these problems will be able to use a calculator, but for now it looks like we can simplify. Now we're going to apply it. Read along with me as I read out loud. Radioactive decay is measured in terms of half-life, the number of years required for half of the atoms in a sample of radioactive material to decay. The half-life of plutonium is 24,360 years. Suppose that 10 grams of the plutonium isotope was released in the Chernobyl nuclear accident, the worst nuclear accident in history, which happened in 1986 at the Chernobyl nuclear plant near Kiev in the Ukraine. How long will it take for the 10 grams to decay to 1 gram? So first of all, if we are studying growth or decay, unless it's specified otherwise, we are going to assume that the rate of whatever is decaying, the rate of the decay, is proportional to the amount that's there, which means dy dt equals k times y. So again, unless otherwise specified, if it's some type of growth or decay, we can assume that differential equation, the rate of decay or growth, is proportional to the amount that we're measuring. Now, ultimately, I'd like to know what I need to find. How long, so that's a question for what time is, will it take for the 10 grams to decay to 1 gram? So if y is the amount, that's the amount, then I want to know what's the t when the y equals 1. That's my goal right there. If I know dy dt equals k times y, immediately I write the solution y equals ce to the kt. Then I have to figure out the constants like we did in the previous problem so that I can find the time when y equals 1. Now remember, in this equation, the c represents the initial amount. Notice in the previous problem, t equals 0 and y equals 2. T equals 0 gives us the initial amount of 2. Therefore, c has to equal 2. We plugged it in and did it the long way, but we don't have to do it that long way. So let's find out in the problem where they tell us the initial amount. In the question, how long will it take for the 10 grams to decay to 1 gram? We start with 10 grams. Or we could read it earlier. Suppose that 10 grams was released in that accident. Therefore, C is 10. That's the initial amount. Okay, initial amount. Now we have to figure out the K. Where is some other information? The half-life. They told us that it takes 24,360 years, that's a time, for half to decay, for half of what we started with. Well, if we started with 10, half of 10 is 5. This is half of what we started with. Half of what we started with for here, our initial amount here, and the half-life 24,360 here. Now we can solve for k. I'm going to divide by 10, 5 divided by 10, or 1/2 equals e to the k times 24,360. Then we need to take the natural log so that the e goes away and I'm left with just k times 24,360. Solve for k. Natural log of 1/2 divided by 24,360, or rather 1 over 24,360 multiplied to natural log of 1/2. Why did I write it that way? Well, remember in the last problem when we were simplifying, it made it much easier when the natural log came first. Let's see why. Y equals 10 e to the, k is all of this number, natural log of 1/2, and then 1 over 24,360 times t. Now you can see why we wanted the e and the natural log of 1/2 to be right next to each other. I can pull the 1/2 down as the base now. Y equals 10 and then 1/2 times, and I'm just going to write this as t over 24,360, a little simpler. Now I don't have to do the simplifying because ultimately I will have a calculator, but still typing it in the calculator, it's going to be easier if there's less stuff to type. So here's my equation, and now I can go to what I need by using that equation. When y equals 1, so my y I stick 1, or substitute 1, t I don't know, so I leave it as t. I need to get that t by itself, so we have to do some moving over. Divide by the 10, and then I have to get the t out of the exponent. The way I get things out of exponents is when I have logs. So if I take the log of both sides, preferably the natural log of both sides, like this, natural log of 1/10, and then natural log of 1/2 to the t over 24,360. Writing it that way, with natural log, I'm able to move this down as a coefficient. So now I have natural log of 1/10 equals t over 24,360 times the natural log of 1/2. Now I just have to get the stuff away from the t by multiplying or dividing. Let's continue. I need the natural log of 1/2, which is multiplied, to go away, so divide by it. Natural log of 1/10 divided by natural log of 1/2, and I need this 24,360 also to go to the other side. So we'll be multiplying this by 24,360, and now I have my t by itself. Now I head to a calculator, and I get approximately 80,922.168. Remember, we always have to carry it out at least 3 decimal places. And because this is time measured so far in years, I'm going to say years. Takes approximately 80,922.168 years for this to decay down to 1 gram.